1.3, linear functions, slope, and applications is a basic review of things that you've done all the way since, pre-algebra. So first of all, we're going to look at linear functions. And the first, page number 90, the first row of graphs there are linear functions. Notice that all of the variables in a linear function have 1 as an exponent. Doesn't matter what else is in there as long as 1 is an exponent to the x and the y. Now look at nonlinear functions. Notice that we have radicals, we have exponents greater than 1, and that second one to the left, we have y equals 6 over x. Whenever you have an x in it, or a variable in the denominator place, it makes a nonlinear function also. So linear functions are a function f. I'm reading on the top of page 91. A function f is a linear function if it can be written as f of x equals mx plus b. If it can be written that way, it's a linear function where m and b are constants. So horizontal and vertical lines, which is the bottom of page 91, says horizontal lines are given by equations of the type y equals b or f of x equals b. And what that is saying is if you have y equals b, that means b is the y-intercept, because y equals mx plus b. This is always the y-intercept, so y equals the y-intercept. If we have an equation where x equals a, we have a vertical line, and that vertical line will give us, we can put any number in there for a that we want. Or so if we have x equals 4 and we say x equals 4, that gives me a vertical line right here. And one of the things that you need to realize about a vertical line is it is not a function because it fails the vertical line test. So that would be if x equals a, you'd have a vertical line. When y equals b, you would have a horizontal line. Alright, page 92, the linear function f of x equals mx plus b and slope. So the slope is considered a line's rate of change. Okay, and you guys are all familiar with it being slope equals rise over run. And that's the rate of change. As we go here, we go here, here, over here. We are making a change right here, and then that gives us a line that is on an angle, usually, a slope. And if it's an uphill slope, it's positive. If it were a downhill slope, it would be a negative slope. So in that form, y equals mx plus b. If this were negative, it would go downhill. If it were positive, it would be going uphill from left to right. So actually, what you've learned in the past is that m equals rise over run. But actually, what slope is the change. We're going to use the Greek letter delta for change, the change in y over the change in x. Now I notice the book doesn't do that as far as using the symbol delta, but use it in chemistry and use it in math, which means another way of writing the change of y would be 1y minus another y over 1x over another x. So for instance, if I had 2 points, 3, 4, and 6, 2. Okay, and I called this one y1, and this y2, and this x1, and this x2. So if I wanted to use this formula to find the slope of the line that connects these 2 points together, I would just go y2, which is 2, minus y1, which is 4, over x2, which is 6, minus x1, which is 3. So negative 2 over 3 would be my slope, so it would go downhill. So negative 2/3. One of the key thoughts on page 95, example 2, is it gives us an x equals negative 2. Okay, that's all it gives us. Does not give us a y value. We're used to y, or f of x, equals mx plus b, where m is the slope, b is the y-intercept, and x and y are 2 points on the graph. Well, if this is all I give you, I don't have a y-intercept, and I don't have a slope, and I don't have a y value. So when I don't have a y value, since y is missing, any value for y will do. So if I have my table here, and I have a negative 2, I can put a y value I can put any y value I want. I can put 1, 0, 3, negative 6,327. So when I graph that, my x is going to be negative 1, 2. And if my y value can be any number here, then I'm going to get a vertical line right here. At negative 2, whatever I want for y, which is going to give me a vertical line, which is not a function. And the same thing is true if I have a y value but no x value. So that would be part B. I have y equals 5/2. That being the case, if my y is 5/2, you can put 5/2 an infinite number of times, and all that means is I'm going to put any number I want here for x, since there isn't one, which is going to give me, that's 2.5, a horizontal line through 2.5, and what I'm saying here is my x value can be anything I want it to be, as long as my y value is 5/2 from the x-axis. So that is a function. Which brings us down to bottom of page 99 on applications of slopes. Okay, so slope has many real-world applications. Okay, talking about grade. Grade would be the percentage. So if we have a grade of 2%, it means that this angle right here is a 2% grade. Okay, so such a number is meant to tell how steep a road is on a hill or mountain. So a 4% grade means that the road rises 4 feet for every 100 feet this way. Okay, that's what we get as far as grade is concerned. Alright, so if you look at the picture on page 96 of the treadmill, notice how every 5 feet the elevation of that treadmill is 0.6 feet. So you can get an idea of what the percentage is by taking 0.6 over 5, and that would give you a percentage. Now if you look at example 3, they've got a ramp for the disabled, construction laws regarding access ramps, and you can go ahead and read that as far as the handicap ramp, but they're saying, what is the grade or slope of such a ramp? Well, the grade or slope is going to be rise. Slope is rise over run. And on this particular one, it says for every 1 foot it goes up. It has to have a horizontal run, or every 1 foot of rise over 12 foot of run. So 1 divided by 12 is going to give you 0.083, which is going to be an 8.3% grade. Now where they came up with that decimal, I have no idea. But one of the things to know is the average rate of change, because maybe you've got a graph that kind of looks like this. Well, you can look at each of these, and this gets into calculus, each of these little teeny points here, the distance between those two lines, and determine a slope. But most of the time what you do is you get an average rate of change where you've got a line that kind of goes here and is the average of all the different rates there, and that really gives you a better idea of a constant number instead of having to look at each one individually. So if you look at example 4, the percent of travel bookings online has increased from 6% in 1999 to 55% in 2007. The graph below illustrates this trend. Find the average rate of change. Okay, so at this point we have two coordinates. We've got 1999 and we have 2007. So we have 1999 is our x value, and we have 6% for our increase, and we're going to go up to 55%, but that's going to be in the year 2007. Okay, so what we have is our rise over our run, or our y, our change in y over our change in x. So our change in y is going to be 55 minus 6, that's a change in the y values, over 2007 minus 1999, which is going to be 49 over 8, or 49 over 8, or 6 1/8 for our average rate of change. So that tells us that over that 8-year period, we're going to change about 6 1/8% per year. Okay, example 5 does basically the same thing. Okay, one more example, page number 98. Example 6. An anthropologist can use linear functions to estimate the height of a male or a female given the length of the humerus, the bone from the elbow to the shoulder. The height in centimeters of an adult male with a humerus of length x in centimeters is given by the function mx equals 2.89x plus 70.64, and the function of a female, f of x, would be the female. X would be the length of the humerus. So we're going to take 2.75 times the length of the humerus, and that adds 71.48. I have no idea where they got these formulas, but they're just using them. So we find a 26 centimeter humerus, and assuming it was from a female, so that means we're going to use this formula right there. And we're just going to say, okay, here's our function, length is 26, that's our x value. So we're going to put 26 in here, and we're going to add 71.48. And when we're done, we're going to come up with 142.98 centimeters. All right? So that's what we're going to get for this gal's height. Alright, so that's it for lesson 1.3.